In this video, we are going to do a structural induction example that involves rooted trees. So let's recall that our informal definition of height of a rooted tree is it's the number of edges we must travel along to get from the root to the bottommost leaf, which we sometimes call the bottom level. So here we have two rooted trees. We've seen this in the previous video, but I'm just recapping that example. So in this first one, to get from the root to any of these bottommost leaves, well, I got to travel along one edge, either that way or that way or that way. So that height of that one is 1. And in the second tree, these are the bottommost leaves, and I got to travel along 2 edges to get to the bottom. So the height of that tree is 2. And remember that when we build our EBRTs or FBRTs, these extended binary rooted trees or full binary rooted trees, we have this, definition B1 star B2 to build new trees, rooted trees from old ones. So if I was trying to construct T1 star T2, remember I begin that process by drawing a new root, and then down to the left of this, I draw T1, draw T1, draw T1, draw T1, and then I connect the root of T1 to this new root, and then down to the right of this new root, I draw T2. So I draw T2, which looks like this, and then from that right one, it extends down even further two ways. And then I connect the root of T2 to this new root. So if I determine the height of T1 star T2, I could just count it, because it takes me 1, 2, 3 edges to get to the bottom. So the height is 3. But if I really kind of break down what's going on here, what does 3 equal? Well, I've added a new root, so I have to travel along an extra edge, either down this way or down this way. So I'm going to have 1 plus something. And what determines that something is, well, out of these 2 trees that I'm appending, which one's taller? Which one's got the bigger height? For my example, that happened to be this one. So the way I can express that in general is to write the maximum of the height of B1, comma, the height of B2. Okay, I'm going to put a thought bubble around this. We've seen this recursive formula before, but I'm just recapping it. So that leads us to this recursive definition, which we've seen before for the height of an EBRT. Remember that in the basis step, where we have the empty graph, that's the building block of EBRTs that we start with, we say the height is -1, which is a little weird, but nonetheless, that's the value that we assign to it that kind of makes everything else work below that. If I have a single vertex, the height of that is 0, and we see that in EBRTs, we also see them in full binary rooted trees, these FBRTs. Because if there's a single vertex, well, there's no edges that I could travel downwards along. So the height would be 0. And I think it kind of makes sense that if there's an empty graph, there's even less there than a single vertex. So I'd expect it to be kind of less than 0. Okay, and in the recursive step, if I star B1 and B2, the height of that resulting graph B is going to be 1 plus the maximum of the heights of B1 and B2, which is what we were seeing here. Okay, so that was a quick recap of height. Now let's talk about vertices in a graph, and let's give a recursive definition for this. So if I have B1 and B2, which are EBRTs, and I want to star them together and count the number of vertices in the new graph, well, what I would do is I would first draw a new vertex. And then I would connect that down to the left with, and I'm just going to put a little bubble here for whatever B1 is, the first graph. And then down to the right, I'll connect it to whatever B2 is, and they're not necessarily the same size. Okay, so if I'm trying to count the number of vertices in this new graph, well, I'll have to count however many vertices are in B1. So there's V of B1 in there. I'll have to count how many vertices are in B2. So I will label that as V of B2. And then, well, there's this extra root that I added. That adds 1 to the number of vertices. So the total number of vertices in this new graph is 1 plus v of b1, the number of vertices in b1, plus the number of vertices in b2. Okay, so we have a recursive formula for the number of vertices of b1 star b2. Okay, so now we are ready for a statement to prove. All right, so the example says, let B be an extended binary rooted tree. Prove that the number of vertices will be less than or equal to 2 to the height plus 1, and then that whole exponent thing minus 1. Okay, so, before we get into, the proof of this, let's just do one quick example to kind of convince ourselves like why we expect this, to be true. So I'm going to separate out what we did here. And I'm going to draw kind of like one simple EBRT. So I'll have my root. Each root in an EBRT can have like up to 2 children. So let's say that these both have 2 children and these both have 2 children. So let's say I have this. So in this EBRT right here, I'm going to call this B. How many vertices are there? Well, I could count them up, and it turns out there are 7. And then if I calculate this other side, 2 to the h of b plus 1 in the exponent, and that whole thing minus 1, well, that's going to be equal to the height is 2 here. So I get 2 plus 1, and then minus 1. So I get 2 cubed, which is 8, minus 1, which is 7. Okay, so this is true. The number of vertices is less than or equal to 7. In fact, in this example that I did, they're actually equal to each other. And I chose this example kind of deliberately because at each step, I made each vertex have as many children as I could. I always picked 2 children at every step. I kind of filled it out as much as we could. So this quantity that we have on the right-hand side, it's kind of giving us what's called an upper bound for the number of vertices in the graph. Okay, so how do we prove this? Okay, because it's a statement involving a recursively defined thing, we are going to use structural induction. So structural induction. Okay, and remember that in structural induction, we start with our base step. So in the base step, we try to prove that the statement that we're trying to show, which is this, holds for the basis elements of the structure, the initial elements of the structure. So in the thought bubble here, I've just written, what was the recursive definition of these extended binary rooted trees? So the initial element in the basis step is the empty graph. So I need to show that this statement I'm trying to prove is true for the empty graph. So my base step will involve the empty graph. Okay. So I'm going to label that B equals the empty graph. So if I look at the 2 sides, my left-hand side will be equal to the number of vertices of the empty graph. But the empty graph has no vertices. So that's just 0. Okay. And then the right-hand side will be equal to 2 times the height of the empty graph plus 1. That whole thing minus 1. And we saw in the definition of height that when we have an empty graph, we say its height is negative 1. So this gives me 2 to the negative 1 plus 1. That whole thing minus 1. Ooh, that whole thing minus 1. This is 2 to the 0 minus 1, which is 1 minus 1, which is 0. Okay, so the left-hand side is 0. The right-hand side is 0. So the inequality is true. So we get 0 is less than 0, which implies the base step holds. The base step holds. Awesome. Okay, typically the base step is the quicker part of any type of inductive proof. So now we're on to the heart of it, which is the inductive step. So the inductive step. So let's recall how this works in structural induction. In structural induction, the way the inductive step works is you look at whatever structure you're working with, in this case, extended binary rooted trees, and you look at the rule that you have in the recursive step of that. And what you do is, the recursive step of this says, okay, if you take 2 extended binary rooted trees. You can build a new one by starring them together. And in my inductive step, what we do is we assume that the result is true for these old elements, the old elements that we're starting with, the old elements. So we're going to assume that it's true for the old elements. Okay, so the way I'll write that is, let's let B1 and B2 be extended binary rooted trees, these old elements, such that, and I'm going to be assuming that the statement that we're trying to prove, which is this, is true for these old elements. So I will write V of B1 is less than or equal to 2 times the, 2 to the height of B1 plus 1 minus 1, and that it's true for B2. Number of vertices of B2 is less than or equal to 2 to the height of B2 plus 1, and that quantity minus 1. So we get to assume that this result is true for these old elements, the ones I'm using to build the new one. And the new element is this, B1 star B2. Okay, so what I want to show is that for B1 star B2, that this result will hold. Okay, so let me write that down. I want to show that the number of vertices of B1 star B2 will be less than or equal to 2 times the height of B1 star B2 plus 1 and then minus 1. And I will put a thought bubble around this. This is what I want to show. I don't know this yet, but that's my goal. I use this thing that I'm assuming to be true, and hopefully using that, I'll be able to show this eventually. Okay. So I'm going to highlight these two things that I assume are true. I'm assuming this is true about B1. I'm assuming this is true about B2. Okay. So now let's talk about, well, how will we show this thing that I want to show? I'm going to flip it to the next page. And, okay, I'm trying to show this inequality. So let's start with one of the sides. Maybe I'll start with this left-hand side. And to do that, I need to now consider the new graph, B1 star B2. And I'm going to call that B. So then, let's take the number of vertices of that. The number of vertices of B1 star B2, well, I have a formula for that, right? We derive that up here. It's 1 plus the number of vertices in B1 plus the number of vertices in B2. So this equals 1 plus the number of vertices of B1 plus the number of vertices of B2. Okay, so we had that. Okay, that was our formula from up above. What can I do with this now? Well, now I get to use these two inequalities about V of B1 and V of B2. So this is going to be less than or equal to, this 1 just stays there. And then number of vertices of B1, well, that's less than or equal to 2 to the height of B1 plus 1 minus 1. I'm going to highlight that in green, just so it matches the way I was highlighting it above. And then the number of vertices of B2, I'm going to replace that with something that's bigger than it, which is 2 to the height of B2 plus 1, and then that whole thing minus 1. So let's highlight that as well. So overall, what I've done is I've replaced these two quantities with stuff that's bigger than each of them. And that's why it gives me this inequality here. Okay, so we have this. All right, so, okay, I can simplify this a little bit because, you know, I got this 1, minus 1, minus 1. I can combine those like terms. So this equals, I got 2 to the height of B1 plus 1 plus 2 to the height of, 2 to the height of B2 plus 1. And then the 1's combined to just make minus 1. Okay, so we have this. So I'm hoping that if I keep working with this, eventually I can make this right-hand side look more like the right-hand side of what I'm wanting to show. So I'm going to do some scratch work here on the side now. If I think about this right-hand side of what I want to show, this is 2 to the, and the height of B1 star B2, well, we have a recursive formula for that. That's this 1 plus this max thing. So that would be 2 to the 1 plus the max of the height of B1, comma, the height of B2. And then I still have this other plus 1 that was in the exponent. And then that whole thing minus 1. So, this is the same as this, if I use my recursive definition. So maybe I could try to make my right-hand side look more like this. Okay, so here's a key idea now. So we know that the height of B1 and, so I'll put comma, the height of B2, well, they are both less than or equal to the maximum height. They're both less than or equal to the height of B1, height of B1, comma, the height of B2. So what I'm going to do now is I'm going to replace both of these heights with this maximum. And when I do that, it makes these quantities bigger. So it'll keep this inequality going. So this is going to be less than or equal to 2 times, I'll get the maximum up here, the maximum height of B1, comma, the height of B2, and then I still got that plus 1 up there, plus 2 times the maximum height of B1, comma, the height of B2, and then plus 1, and that whole thing is minus 1. Okay, well, now I have the same term twice. So I could just write that as 2 times that term, 2 times 2 to the maximum of the height of B1, comma, the height of B2, plus 1. And then I got that minus 1 at the end. Okay, so one thing I notice is, wait, 1 plus this maximum, well, that's just 1 plus this maximum. Let's go ahead and replace that. That's just 2 to the h of B1 star B2. That's my recursive definition for the height of B1 star B2. So I got that times 2, and then there's that minus 1. And when I multiply these two terms, I add their exponents together. So that'll be equal to 2 to the 1 plus the height of B1 star B2. That whole thing minus 1. And now if I look back up to what it is that I wanted to show, well, let me zoom it out. I got the right-hand side. Okay, so I started with the left-hand side, number of vertices in B1 star B2. And at each step, I either said what it was equal to, or I have this inequality, a less than or equal to. So what that means is this thing that I started with is less than or equal to this thing that I ultimately just ended up getting. Okay, so let me just, because this is such a long chain, let's just state that. So thus, the number of vertices of B1 star B2 is indeed less than or equal to 2 to the 1 plus the height of B1 star B2, that whole thing minus 1. As desired. That is what we wanted to get. So then I just write my conclusion, which is by structural induction, the result that we wanted to prove holds. The result holds. And there we have it. So one quick comment that I want to make about this is there are a bunch of results about, rooted trees and graphs when they have recursive definitions that we could prove using structural induction in this way. So that's one of the things that makes this a really useful tool.